So today we're going to look at what's called the second derivative test for finding relative extrema. And it incorporates both finding where there's horizontal tangents and also looking at concavity, okay? So right here at this point on the graph of, let's say this is the function f, right here at point A, there's a horizontal tangent right there, okay? So because if we look right there, okay, we can tell that f prime of A is equal to 0 because the tangent line right there would be horizontal, okay? And if we look, that point is in some interval in which the graph is concave up. So that would mean f double prime of A is greater than 0, okay? Then looking right here at this point B on the function, all right, once again, we look there and go, okay, there's a horizontal tangent there. Well, that would mean f prime of B equals 0. And right there, we can't tell the concavity of it because right before it looks like it's concave down and then right after concave up. So that looks like a point of inflection. So that would mean f double prime of B equals 0 also, okay? And then at point C right here, okay, at point C right here, there's another horizontal tangent right there. So f prime of C would equal 0. And we can tell that that point is in some interval that in which the graph is concave down. So that would mean f double prime at C would have to be negative or less than 0. Okay, so this really doesn't tell us anything about extrema, but this one does. So if you find a place where the derivative is 0 and the second derivative is positive, that would mean it's concave up and it would have to have a relative minimum right there. Okay, so this function has a relative minimum at x equals a. So we'd say relative minimum. And over here, if the second derivative is negative, then we could say that it's concave down. And then right here at this point, we would have to have a relative maximum. So concave down would cause a relative maximum, and concave up would cause a relative minimum, okay? So right here, this is a relative maximum, okay? All right, and here we couldn't tell, so that's going to be important in just a second. So stating a formal definition of this second derivative test, if f double prime of C is equal to 0, okay, so that would mean we have a horizontal tangent, and f double prime of C is less than 0, okay, so the second derivative at that same value, where the first derivative was 0, at that same value, the second derivative is negative. That would tell you that it's concave down. And then because it's concave down, and I always do like this, concave down, right? And so that tells me, all right, relative max, all right? So I'm using my fingers to help you guys see this, okay? So this means concave down, relative max. I need a visual for it, okay? So that would mean f has a relative maximum at x equals c. And consequently, also, if f prime of c is equal to 0, and again, there's a horizontal tangent right here, f double prime of c is greater than 0. Okay, so now it's I can't do it with my fingers. I usually do this in front of you guys. So this one, f double prime of c is greater than 0. That means it's concave up. It would look like that. So we'd have to have a relative minimum. I always think of like a parabola. Okay, so horizontal tangent, concave up, which means you have to have a relative minimum at that x value, okay? And this one would be concave down, so it would look like this, right? Okay, so that's kind of what I was trying to do with my hand to show you, but I can't do that with dot camera. I usually do that when I'm facing you guys. All right, one more thing, and then we'll do a problem. Okay, so this is important. If f prime of c is equal to 0, okay, so we have a horizontal tangent, but the second derivative at c is also equal to 0, we cannot use the second derivative test, okay? So it fails. It doesn't work for this, okay? Because we can't tell the concavity. We can't tell if it's concave up or concave down. You know, we can't see if it's like this or like that, right? So because of that, all right, we can't use this second derivative test because we don't know the concavity right at C. And we don't know if that point is in an interval where it's concave up or concave down, okay? In this case, we'll have to use the first derivative test. So we'll have to go back to making a sign chart, okay? And looking at the intervals. Now, where this is happening, we just need the interval to the left of this point C and to the right. We don't necessarily have to make a full-blown sign chart. And you'll see that in just a second. So here's a first example. Let me try focusing it a little bit better. Okay, so find the relative extrema for f of x equals negative 3x to the fifth plus 5x cubed. Okay, so looking at this, all right, let's figure out the domain. Well, this is a polynomial, and the domain for all polynomials is negative infinity to positive infinity. So we always need to look at the domain for this, okay? Because if we get a critical value, all right, and it's not in that domain, then we can't use it, okay? All right, so now we gotta go about finding the first derivative, okay? And we're doing this in order to figure out, okay, where are these horizontal tangents, okay? So to take the derivative of this, that would give us negative 15x to the fourth, and then plus 15x squared. Okay, so we want to figure out where is f prime of x equal to 0. So that would mean negative 15x to the fourth plus 15x squared is equal to 0. Okay, and so what we could do here is factor out a negative 15x squared, and we'd be left with x squared minus 1 equals 0. And then we should notice right here, oh, that's a difference of squares. So that makes negative 15x squared times x minus 1 times x plus 1 equals 0. Okay, so to solve this, this would happen when x equals 0, when x equals 1, and when x equals negative 1. Okay, so our function definitely has horizontal tangents at x equals 0, x equals 1, and x equals negative 1. Now, let's figure out the concavity, and let's see, is this a point on an interval in which it's concave up or concave down? And then same thing for each of these. So the way we can do that is to plug these values into the second derivative. So what do we have to do? Find the second derivative, okay? So f double prime of x, the second derivative with respect to x would be negative 60x cubed, and then plus 30x. Okay, so now we need to find f double prime of 0, of 0. And that would be negative 60 times 0 cubed plus 30 times 0. Well, that would equal 0. Okay, so that means we can't use the second derivative test on this one point, right? So we're going to have to do the first derivative test at x equals 0, okay? So we would say second derivative test fails. Okay, so we can't use it there. How about f double prime at 1? Okay, so f double prime at 1 would be negative 60 times 1 cubed plus 30 times 1. Okay, so this would be negative 60 plus 30, so that would give you negative 30. That's negative, so that's telling you it is concave down, okay? Okay, so if it is concave down, that means there's a relative max at x equals 1. Okay, so now we need to find f double prime of -1. So that would be -60 times -1 cubed plus 30 times -1. So this would be -1. When you cube -1, you get -1 times -60. So that'd be 60. And then this would be minus 30. Okay, so that would give you positive 30. And so that's telling us that it's concave up. All right, so since it's concave up, then this would have to be a relative minimum. Okay, so we have a relative min at x equals -1. Okay. All right, so we've already determined, I mean, we're gonna have to do a little bit more in our justification, but we know we have a relative max and a relative min already. Okay, but we don't know what's happening at 0. It could still be a relative min or relative max. It's just we can't use the second derivative test to figure it out. Okay, so that means we have to go to the first derivative test. So we have to make some intervals. And that would be, we start with our domain, -infinity, up to the first one, which would be x equals -1. So -infinity to -1, and then -1 to 0, and then 0 to 1, and then 1 to infinity. And we would look at a test point. And right in here, this would be x equals -2. That's what I would use. X equals -0.5. X equals 0.5, and x equals 2. Now, I meant to say this earlier. We're also going to talk about the sign of f prime, and then that will tell us the behavior of f. Now, we already know what's happening at -1. So really, we don't need this interval at all. Okay, we do need this one. Okay, and we need this one because this is the left side of x equals 0, and this is the right side. So we're going to need to use these two intervals, but we also don't need to figure this one out. Okay, so that's just extra work that we really don't have to do for this problem. Okay, so if we put -0.5 into the first derivative, and probably the easiest one to always put it into is the factored one, okay, to do this mentally. So we have a negative x value, so when we square it's going to be positive, times -15, so that's going to be negative. And then when we put -0.5 in here, the second factor is going to be negative. And the third factor, when we put -0.5 in there, it's going to be positive. So we have a negative times a negative, which is a positive, times a positive, which is positive. Okay, so the behavior of f tells me that's increasing. And then at x equals 0.5, when I square it, that's going to be positive, times -15, that's going to be negative. And when I put 0.5 into the second factor right here, that's going to give me 0.5 minus 1. That would also be negative. And then 0.5 into this third factor would give me a positive value. And so we have a negative times a negative, which is a positive, times a positive, which is positive. So it's increasing there. Okay, so it's going from increasing horizontal tangent to increasing. So that's not a relative max. So now we know for sure, without a doubt, that x equals 0, there isn't a relative min or relative max. Okay. All right, so let's do a little bit more work. Okay, we need to find the actual outputs for f of 1 and f of -1. Okay, so f of -1 would equal -3 times -1 to the 5th plus 5 times -1 cubed. Okay, so this is going to be negative, so this would equal +3, and that's going to be negative, so -5, and that would be -2. And then f of 1 is equal to, okay, so if we put 1 in here, that would give me -3 times 1 to the 5th plus 5 times 1 to the 3rd. So this would be -3 and then plus 5, which would give you 2, +2. Okay, so here's our justification, okay? So this is how you have to write it up if you're going to use a second derivative test. So we have f of x has a relative maximum at, or of, sorry, maximum of, and this is happening at x equals 1, so x equals 1, it's 2. So a relative maximum of 2 at x equals 1 because, and it's because f prime of 1 is equal to 0. That's the horizontal tangent piece. And f double prime of 1 is less than 0. I should have wrote and in here. And f double prime of 1 is less than 0. And that's justification for why there's a relative max there. All right. So then we have f of x also has a relative minimum of, and it's happening at x equals negative 1. All right. And at x equals negative 1, the output is negative 2. So there's a relative minimum of negative 2 at x equals negative 1. And because we know f prime of negative 1 is equal to 0, and I remembered it this time, f double prime of negative 1. And so it was a relative minimum because we saw that it was going to be concave up, which means the second derivative was greater than 0. Okay. And then you wouldn't have to, but you could also say there's no relative extrema. At x equals 0. You wouldn't have to say that though, because I just asked you where they were. You don't have to tell me where they're not, because if I ask you for where they're not, well, that's like an infinite number of points, right? So you don't have to say this. Okay, I'm just adding that in for the lesson. Okay. All right. Let's look at another problem here. So for this problem, we want to find the relative extrema for f of x is equal to x times ln of x, okay? So there's a domain restriction here, and that is because there's a logarithm function, and we know that logarithms, that the argument here, the x, has to be positive. So that means this x has to be greater than 0, which tells us the domain for this function would be 0 to infinity. Okay, so if we get an x value for the derivative being 0 at an x value that's not within this domain, then we're not going to use it. Okay, there's no point in it because the function doesn't even exist at 0 and to the left of 0. Okay. All right, so here we go. We're going to find the first derivative. So to find the first derivative, that would be f prime of x. And because this is a product of two variable functions, we're going to have to use the product rule. So the derivative of x is 1 times the second function, which is ln of x, and then plus x times the derivative of the natural log of x, which is 1 over x. Okay, so that means f prime of x is equal to ln of x, and this would be x over x, so that'd be plus 1. So again, I'm going to try to use the second derivative as much as possible. Okay, second derivative test, that is. F prime of x is equal to 0. That would mean the natural log of x plus 1 would have to equal 0. Okay, so recall solving logarithms, we're going to have to isolate the natural log of x by itself. So I need to subtract 1 from both sides. So that'd be the natural log of x is equal to negative 1. And then to undo logarithm, we exponentiate with a base of e. So this is going to be my power. E to this power is equal to e to this power, okay? So e to the ln of x is equal to e to the negative 1. These undo each other, and we're left with x equaling e to the negative 1. Now, what does a negative exponent mean? It means reciprocal, right? So this means x is equal to 1 over e. So the value of 1 over e, okay, and that is a positive value because remember, e is about 2.7 something, right? So this is 1 over 2.7, which is within the domain here, okay? All right, whew, okay. All right, so we found this x value right here. There's a horizontal tangent there, okay? So is there relative min or relative max there? Okay, the way to do it is to look at the concavity at this particular x value. So that means we're gonna have to find the second derivative, okay? And actually the second derivative is easier to find. So f double prime of x is simply, okay, the derivative of natural log of x, which again is 1 over x, plus the derivative of 1 with respect to x, which is 0. So I don't even need to bother writing it. There it is. That's the second derivative, okay? So then, okay, let's see if we can tell the concavity of it, okay? So that means f double prime of 1 over e. Well, that'd be 1 over e. So that's a complex fraction. So I'm going to multiply this fraction by e over e, and that makes the top or the numerator become e and the denominator 1. So that's just e. Okay, so our output for the second derivative is e. And you recall that e is about 2.7 yada yada, right? And what matters is that it's positive, right? So because it's positive, that means it's greater than 0. That means it's concave up. That means relative minimum, okay? All right, so e is positive, which means f double prime of 1 over e is greater than 0. And when it's greater than 0, that's concave up. And when it's concave up, it looks like that. So that's why a relative minimum. I always use a parabola to determine like to help me picture, okay, concave up and concave down, okay? All right, so we know it's concave up. So if it's concave up, that means we have a relative minimum at x equals 1 over e, okay, because we have a horizontal tangent and we know it's concave up, okay? So now what we need to do is we need to find the actual value, okay? So f of, and we're finding it at 1 over e, so that would be 1 over e times the natural log of 1 over e. Well, that would be 1 over e times the natural log of, and we always want to write, if we have natural log, we want to write this as e to a power, and we can. So that can be rewritten as e to the negative 1 power. And the reason we want that is because these are going to do each other, and you're going to be left with negative 1. So this is 1 over e, and I just realized I'm running out of space. So this is 1 over e times negative 1, or that is just negative 1 over e. Okay, so what does this mean? This means f of x, we can make our justification, f of x has a relative minimum of negative 1 over e at x equals 1 over e, because f prime of 1 over e equals 0. That's the horizontal tangent piece. And f double prime at 1 over e was positive, right? It was greater than 0. And that's why we know there's a relative minimum there. And that's it. There's no relative maximum. Okay? All right. And that's, so you got to put the value that you find, okay? And you got to show that when you put that value into the function, it gives you 0. And when you put it into the second derivative, it's either going to make it be positive or negative. So greater than 0 or less than 0. Okay? All right. That's the lesson for today, guys.